Thank you very much.
So, to give a talk here. So I slightly changed my mind, and I originally planned to give some survey on quantization of symplectic varieties, but maybe more specifically I will talk about Coulomb branch of supersymmetric gauge theory. So this is my attempt to, so supersymmetric gauge theory. In fact, this is supersymmetric gauge theory in 3 dimensions. Is a subject of physics and not really mathematics. But they somehow consider the Coulomb branch of supersymmetric gauge theory, which is a certain symplectic variety. So some years ago, I started to consider a possible mathematical approach to this problem. So I tried to give a definition of this symplectic variety by a purely mathematical method. And as a byproduct, it also gives a quantization of symplectic varieties. And it seems, so this quantization is a certain noncommutative algebra, which is a deformation of the coordinate ring of symplectic variety. And this noncommutative algebra includes many interesting examples of noncommutative algebra which have been studied in representation theory. So I think this Coulomb branch gives interesting point of view to this study of representation theory. And for most of the algebraic geometries, so you may not interested in representation theory, but somehow I think my method, by the way, so this is based on joint work with Reberman and Finkelberg. So our construction of symplectic variety is something very interesting, and we construct a variety in a way which is I never see in other contexts. So we construct symplectic varieties. And their quantization. By homology group or modular space. Or bundles. So modular space of bundles are important objects in algebraic geometry, or even also differential geometry. And the people are interested in its modular space and its homology group. And people try to extract invariants from homology group. But the invariants are just numbers, and sometimes you can construct algebras, which is algebraic structures, and sometimes categories. But rather than I constructing those algebraic objects, I construct space from this homology group. So this is I don't know this kind of construction appears in other contexts, but so for example, so I believe this construction may be useful in other contexts. For example, in mirror symmetry, you just remember the mirror symmetry. Mirror symmetry says that so Gromf-Witten invariant of certain Calabi-Yau manifold is given by period of mirror Calabi-Yau. So usually, I mean, you start with you take Calabi-Yau, you just say that we know the mirror. So you don't need to construct the mirror. But if you view in a different way, you can regard this mirror is constructed from this Gromov-Witten invariant of the original calabrian. So in that sense, I mean, you must really construct variety from this kind of modulations. So in this setting, the construction is simpler than the one required in mirror symmetry. So I hope, but still, I mean, I hope it may be some hint for the application to another situation. So anyway, I start with baby model. In fact, this is the very first example of a Coulomb branch. So I construct a space, symplectic space in 3 steps, symplectic variety in 3 steps. So I first consider the homology group, or homology group of complex projective space. So this, I hope everyone knows, this is just the ring, polynomial ring of one variable divided by n plus 1. So by some reason, I did not variable by y. So you can consider this to be a space. This is just point with multiplicity n plus 1. So this is a kind of construction of space from homology. But I mean, of course, this is not interesting space at all. So you must do something. And in this particular case, you can take n, limit n goes to infinity. So then you can recover basically C of y. So this spectrum of C of y is affine line. And in fact, there is a systematic way to take the limit, which is called equivalent homology group, cohomology group. And this CPN is a finite dimensional approximation of the classifying space. So you consider equivalent homology of C star of point. So point is CPN is a Cn plus Cn plus 1 minus C star over C star. So this, if you take the limit of this, then it has no homology, and this is a bound. So this is so-called classifying space, classifying boundary. So anyway, so this is polynomial in one variable. So this is the first step. And second step. So in some way, if you just consider the usual variety, you get a finite dimensional vector space with ring structure, but corresponding spectrum is just Artinian and scheme, so it's not so interesting. So you must do something. So here I take the limit. So I consider basically infinite dimensional variety. But instead, you can also consider infinite many components. So this is a trivial example. So you consider those points parameterized by integers. And I consider its homology. So this is just, of course, I mean, this is a point, so there's no homology at all. So this is trivial homology group. But you can define an operation. So you have f, which is given by addition. So you can consider H star of x as a group ring for integers. So you can, so what that means that you can define push forward with respect to this addition. So this is again algebra, gives multiplication, and h star of x is algebra. And so if you consider the fundamental cycle for point mth point, and fundamental class for nth point, and if you push forward, so this is just fundamental class for m plus n. So h star of x is just isomorphic to polynomial in Coulomb polynomial ring xx inverse, so that n, fundamental class of n corresponds to x to n. So spectrum of h star of x is C of xx inverse. So this is C star. So this both are not symplectic, but you just combine you get symplectic variety. So H star equivalent S1 C star equivalent homology of this X. So then this is just C Y X X inverse. So this spectrum is C cross C star, and it has symplectic form. So this is Y and this is X. So dx x which dy. So this is symplectic. And in fact, this is the Coulomb branch of the pure gauge. So I use the C star, which is a complication of this compact Lie group E1. So this looks a stupid construction, but in fact you can generalize. So this gauge theory is assigned for pair. So G is a complex reductive group, and N is its complex representation. Then you can assign supersymmetric gauge theory, and you can define the Coulomb branch, its Coulomb branch. And I take just G to be C star and N to be zero representation. That pure means the zero representation is zero. Then this Coulomb branch is homology group of this, equivalent homology group of this space X, and this spectrum is sequence. So any question? So before I explain the construction, I explain quantization. So suppose X omega is a symplectic manifold. So I'm considering a symplectic manifold in complex category of complex manifolds, not real symplectic manifold. Then you can define Poisson bracket. So omega is a symplectic form, so this is closed non-degenerate two form. So its inverse can be considered as lambda 2 T star of X, two form on to form own differential forms. So you can define a Poisson bracket. So Poisson bracket of f and g is omega inverse of df and dg. And you can use a closeness of omega to check that this satisfies the Jacobi identity. So this is a real algebra. So f and g is functions on x. So I denote this coordinate ring of x, this C of x. So I mostly consider the case when x is an affine variety. And in fact, there is some slight modification of the construction. Case a projective variety, but today I only consider the affine. So this coordinate ring becomes the so-called Poisson algebra. So which means this is a commutative algebra, and you have this Poisson bracket, which satisfies compatibility like so f and gh is equal to f g times h plus g times fh. So this f Poisson bracket by f acts by derivation. So this is a compatibility condition. And there is a general notion of Poisson algebra. Poisson algebra is a commutative algebra with this Poisson bracket, which satisfies Jacobi identity and this derivation. And once you have a Poisson algebra, you can ask its quantization. So this is, I denote by AH bar. So this is a algebra over CH bar. Or you can consider the algebra defined over formal power series also. So this is a non-commutative, in general, non-commutative algebra. And the condition is, so this is the definition, algebra A of 0 is this, of course, A of h bar at h bar equals 0 is equal to A of 0. So this non-commutative A of h bar is a non-commutative deformation of a commutative algebra, and Poisson bracket is given by this formula. So take f and g from A0, then you lift it to h bar and consider the commutator. So this, since this is non-commutative algebra, this may not be 0. But at h bar equals 0, this vanish, so you can divide this by h bar. And then you specialize at h bar equals 0. So this is the definition of Poisson bracket once you have this non-commutative algebra. Or other way around, you can start with non-commutative algebra, which is becomes commutative at some special point. Then you can define Poisson bracket in this way, and you get the Poisson algebra. So this quantization is inverse converse construction. Starting from Poisson algebra, you ask there exists a non-commutative deformation such that one Poisson bracket is given this. And so usual construction is and in many, I mean, Koncevich proved quite a general scenario. So you start with Poisson manifold. So Poisson manifold is, I mean, so you don't require omega to be non-general, but omega inverse is well defined. Then you can have Poisson bracket on here, and then concept which show the existence of quantization, at least of a formal path. But I'm interested in the representation theory, so this is some general construction. I really want to have more concrete examples of quantization and symplectic variety. That is of my interest. So better to have some more explicit construction. And at least for x is equal to x when the variety. By the way, so at the beginning I assume x to be smooth, but once you go to this, and if you assume normality, then you can define the product only on the function which is defined on the regular locus. So the smoothness is not so important. So anyway, here I assume M to be again smooth, and I consider its cotangent bounded, and dm is a ring of differential operators. And then this is a quantization. Or more precisely, maybe specialized at h bar equal 1. So for example, even more concretely, so I have variable x, and I have differentiation x dx. So this is equal to 1. So, or minus 1 maybe, which is d dx. Yes, this is 1. So you multiply this by h bar d dx 1 x is equal to 1. No, not h bar. So at h bar equal 0, it becomes commutative. So you can just formally take this to be limit h bar equal 0 to be y. So then you get the commutative ring Cxy with Poisson bracket yx equal to 1 by this. So this case, the symplectic form is just a dx dy. And so exercise is just to realize this. So this C star of T, where it is, yes. C cross C star is a cotangent of, this is cotangent bundle of C star. Baby model. C cross C star is cotangent bundle of C star. So this symplectic form is natural symplectic form of a cotangent bundle. And so I realize this by equivalent homology of some space. So exercise is just to consider H star of C cross C star cross C star on the same space. But you must slightly modify the action. Use to construct quantization. So this quantization, I mean this canonical quantization given by differential operators. And so in our construction definition of Coulomb branch, which I will explain now, gives also the generalization of this solution of this exercise. So any question or comment? So because this vanish at h bar equals 0, so you can, I mean, this is how to say, there's more precisely, there's element which is, if you multiply h bar, it becomes this element. So that is what I really mean by divide. And then this element, if you specialize the h bar equals 0, this is well defined independent of choice of the lifting of f and g into the different. Yeah, yeah. Otherwise, you don't. If you don't choose lifting, this formula doesn't make sense. This is originally this is commutative. Okay. So and then you got the non-commutative algebra to consider commutator. Okay. So this if this you stay in the commutative algebra, this is 0.
I see.
Okay. I can erase. So I mentioned that this I consider the gauge theory in 3 dimensions. So this is real 3 dimension. So, but the 3-dimensional gauge theory gives, so you consider a partition function after introducing a certain algorithm. This is a number. So you can, so I hope you have, you may heard about this topological quantum field theory. So 3-dimensional quantum field theory associate numbers to 3 manifold. Maybe I don't know what is the right notation. So this is real 3 manifold. So this number by partition function. But if you have 2 manifold, then instead of a number, you assign a vector space. So this is a construction of the quantum field theory. And so expectation is that if you consider 3 manifold, which is decomposed into 2 pieces like this, then this is a common boundary of M1 and M2. More precisely, this is opposite orientation. So so I denote this by Z of sigma and Z of M. So Z of M is pairing between Z of M1 and Z of M2. So this is an element in Z of sigma, and this is an element, Z of M2 is element in Z of opposite orientation, which is dual space. So, I mean, unfortunately, this quantum field theory is a physical theory, so there is no mathematical axiomization of this quantum field theory. I mean, maybe you may have about conformal field theory that is 2-dimensional theory. So then people somehow understand mathematical approach to 2-dimensional theory. But this is a higher dimension, so it becomes more difficult. At this moment, no one can really give an axiomatic definition of quantum, mathematical rigorous definition of quantum field theory in 3 dimensions. But somehow I use idea of from this quantum field theory, and I give a mathematical definition of Z of sigma in using gauge theory. And this, because this is sigma is a two-dimensional manifold, so I consider the gauge theory on 2 dimensions to construct some vector space. So anyway, I start. So G and N as a both complex reductive group, and then is representation of G. So I consider sigma. So I put the Riemann complex structure as this. So this is a smooth projective curve. And I also take line bundle over sigma. Then I consider M, so which is moduli stack of L twisted pairs. On sigma. So this is a pairs of G bundles and section of some associated vector bundle. So P is G bundle. And S is a section. So you can, so P is a G bundle, and if you have a representation, you can consider the associated vector bundle, which I denote by this way. So this fiber of at each point is N, but it is twisted around according to this principal bundle. And I twist it by L and divide by isomers. So this is modular stack. And I don't put any stability condition. So for example, if G is if G is, for example, GL2 and N is vector representation. This is a modular space of pairs. So this is considered radius, and in higher dimension, Brador. And so this is a pairs of vector rank n vector bundle and its section, sometimes twisted by this line bundle. And also, if you take just the arbitrary G complex reductive group, and N is adjoint representation. So this is the representation, the Lie algebra. And L is the canonical bundle. This is Hitchin's modular space. But for any choice of group and any representation, you can consider this kind of modular space. So I consider using the idea of the convolution to that operators acting on the homology of group of this space. Operators acting on homology group of modular space via convolution. And there's a natural one, the so-called Hecke correspondence, so which has been used. I mean, original Hecke correspondence is just the correspondence for the moduli of elliptic curves. But similar construction has been used in the context of vector bundles, and that also can be applied to this setting. So it's goes like this. So fix a point in sigma. Then consider the correspondence. This is called in the original context, this is Hecke correspondence, and I still continue to call Hecke correspondence. So I consider pairs P1, S1, but I consider two pairs, P1 and P2, S1, S2. And the assumption is that this, and also there's another data, phi. So phi is isomorphism of P1 and P2 outside the origin, outside X. And this section S1 is sent to S2. Again, this is isomorph. So it means that the P2 is obtained from P1 by some kind of modification at X. And for example, this is line bundle. This is just given by multiplication. So if I take a coordinate Z around X, so maybe auto. So this maybe the X coordinate is X, then X to the power n, and to be integer. So this is an example of modification. So implicitly in this division, n I don't fix n, so n can be arbitrary. So this is scheme infinite type. But anyway, so you must, as the baby example, you must allow some infinity. And you have two projection m cross m to m. So just taking first pairs and the second pairs. And you can define operator by, if you have a homology class here and you pull back and then push home. So this gives operator. And in fact, because this is just a modification at point, so you don't, global structure of Riemann surface is not relevant. So you can just replace this by formalities, replace sigma by formalities. So this. So you consider the same modulus, the same definition. Now P1 and P2 are G bundle defined over formal disk. So I denote this space by R. So because I really don't, to construction, I only need algebra, not its representation. So I can replace this. Then the first proposition is one can endure the convolution product on H star R. So this is basically, you consider D, so P1, P2, P3, and S1, S2, S3 over D, and you have the isomorphism, which is defined over the functional disk. So you remove the origin. Phi 1, 2, phi 2, 3 is defined except the origin. And then you put the same condition. Then from this space you have 3 projections to R. So just take P1, 2 and P2, 3 and P1, 3. So if you have a homology class here, then you pull back to here and by P1, 2 and P2, 3, and then push forward to P1, 3. So this gives convolution product. So you must be a little bit careful because R is not smooth. So you need to check that this pullback is well defined. But you can do.
Sorry, can you say again what is
R? R is a space. This space. But I replace sigma by the formal disk.
So the reason why you pick the quant is that because otherwise you wouldn't expect any isomorphism to exist, or like it might be empty.
Well, I mean, you can consider more generalization probably, but it gives just different correspondence, and this is a kind of correspondence in the product of the modular space which people successfully study. So you just modify. I mean, for example, so all the well, how to say. Yeah, I don't have a good explanation, but this is anyway, so example of modification correspondence of the product, which seems to be very natural. Is it okay? Any question? Yes? So this is, I just replace curve by formal disk. It doesn't depend. Yes.
And you can think about the representation for those modules as groups. So the modules are representation spaces. So is there like a larger group study of like invariance in TQFT?
So far, this is a part. I mean, my ultimate goal is to construct this TQFT, but so far I can construct a very small particular Hilbert space associated with S2. So this is a small part of the construction.
My question was, what exactly it means to replace sigma x by this homologous 2? You still look at operators over sigma, or maybe
No. So this P1 and P2 are just defined over the disk. That is enough. P1 and P2 are over the disk, S1 and S2 are defined over disk. Phi is defined over the functional disk. Where is the proposition? And the second proposition. Second proposition is a little bit surprising, but well, I don't remember. So this is until 9, huh? Until 12, right? Yes. So this is commutative. This product is commutative. So heuristic explanation is, I mean, you cannot really write 2 points in configuration space, but somehow you just form you must really, yeah, maybe I cannot really. So if you consider the modification at 2 points, then you can consider modification at 2 different points. That is isomorphic to modification at the same point. So this is a deformation, and product is invariant in the deformation. You can consider in this situation. So this is the first product, and the second. So then, if you have 2 points, there is no distinction. So it is a heuristic reason why this becomes commutative. And you can break this symmetry. So you consider the C-star action on the disk. So this is the loop rotation. Loop rotation. Then you have natural action. This action extends to C-star action on the space R. So you can consider equivalent homology of space this R. So this is a deformation over of H star of R over equivalent homology of this C star of point. So which is polynomial ring in one variable, as I first mentioned. So the theorem is, so this is commutative algebra and this is non-commutative deformation. So this, because once you consider the rotation, you cannot write this picture. So product is no longer commutative. So this is commutative, non-commutative deformation of commutative algebra. So I just define a Coulomb branch as the spectrum of this commutative ring, and A of H bar as just H star C star of R. And we show that this is symplectic. I mean, in general, this has singularities. So this is symplectic. First of all, this is a Poisson algebra by this construction, which I just explained. And it is symplectic on regular locus. And this is a quantization. So this is our construction of symplectic variety. Okay, then in the remaining minutes, so I give examples and properties. So first, you just recover baby model. So you take, as I said, you just take G to the C star and N to be 0. Then, as I mentioned in here, so the bundle, line bundle, I mean, in fact, any G bundle over this is trivial. So, and phi is just given by this one, and so it has some non-trivial reduced structure, but I'm considering homology group, so that is irrelevant. And this is just so bunch of points, this xn. But you must divide by automorphism of C star, and this is the example. So I consider this is a Artin stack, but so this Artin homology of Artin stack is just equivalent homology. So this. Yeah, maybe this is important, so I keep this. And you slightly a little bit more careful, then you generalize G to be T and N to be 0. Then basically you get the product of, yeah, maybe let me see this. So you get the product of this one. But in fact, this is more precisely, you naturally get cotangent bundle of the dual of this torus. So this T check is dual torus. And the second property is, so you have homological grading on this homology group. So this is in general both finite and both plus infinity and minus infinities, because this is infinite stack. So this is grading values in Z, not positive. So grading on commutative ring gives C star action on its spectrum. So MC has a C star action, and C star action in this example is just the rotation of this C star. Or maybe no, maybe which is maybe. So this is this is probably fiber-wise actions. Let me see which is which. So I have x inverse and y. So it is grading is y has grading 1 and x inverse is, so it is a multiplication on the fibers. Sorry. Scaling section in this, yes. And from R, you can just forget one of the, just pick up this one, and you have homomorphism. So you have equivalent homology of G, or maybe point divided by G of O, automorphism of trivial bundle to H star of R. So this gives me morphism in the opposite direction. So from MC to spectrum of equivalent homology of point GO. So this is just the algebra of T divided by Y group. So T is, so algebra of T is maximal torus. So this is a generalization of projection. So this is C cross C star. So just take this part. Generalization of this, taking this first projection first. And you can show that the generic fiber is dual torus. So in this second example, 1 prime, so this, all the fiber are isomorphic. So this becomes just a product. And in general, this is no longer a vibration, but you can at least say that the generic fiber of this torus. And you can show that this by localization theorem in equivalent homology. So this is a consequence of. So to study the generic fiber, so you just need to, by general property equivalent homology, you just consider the equivalent homology of fixed point. So you take maximal torus and you just take fixed point set. And you can directly check that this, in this definition, if you take torus action and fixed point is just a similar variety just for this example. from this, you just you just showed us this statement. And there are some properties, and maybe the case of Hitch modular space is important, so I just write it. So maybe 3, 4, and then finish. So G equal arbitrary, and N equal adjoint. So this corresponds to the Hitch modular space. In this case, MC is just basically this example, but divided by Y. So for example, if G equals GLN, then this is just C cross C star, take n times and divided by symmetric group of n letters. So this is symmetric powers of the surface. N symmetric powers of the surface C cross C star. And you can, in fact, also construct example which is symmetric powers of C cross C instead of C cross C star. And the Hilbert scheme of points is also constructed in this way. And there are lots of examples which arise in geometric representation theory, which can be example of symplectic variety, which can be realized in this construction. So I stop now. Thank you for attention.
Questions?
What happens if you take integral Coulomb instead? Are all these Coulomb branches naturally defined over Z, or do they have very bad behavior?
Yeah, I don't consider, but Coulomb branch will be defined over D. Yes. Just to replace everything by whole by something. But I don't consider that.
Do you know what happens if you upgrade to like A theory or elliptical module?
Okay, so you get the so-called four-dimensional gauge theory of four-dimensional. And the elliptic model, I don't know, I don't check it. Yes, certainly you should expect you should get the 5 kilometers for 5 dimensions.
Does MC have any natural symplectic resolutions?
In general, no. In fact, you can show that what minimal nilpotent orbit. So I don't mention minimal nilpotent orbit. On type AD, can be constructed from the so-called Quiver reason. It is well known that the minimal nilpotent orbit has resolution similar only in type A. D and D doesn't. So in general, these are done. And our current conjecture is that this MC is only the so-called symplectic singularity in terms of modules, and we don't know how to do it.
What was the role of equating cohomology of this modular space which projects close?
In projective classes, you don't have this action. So you don't see, I mean, unless you consider the P1 and you consider parabolic. So maybe you must have a fixed. So on P1 you don't have. I mean, you don't have. You only get the trivial modular space. But if you allow punctures, then you may have non-trivial examples. But you can put the punctures only 2 points. So you must consider wild singular, wild ramifications. Otherwise, modular space becomes trivial. I suspect that might be something to do with one homology, but so far I don't know.
One less thing, speaking.